Hello, my name is Marom Bikson, and today I'm going to be talking about how transcranial alternating current stimulation works, or tACS. I'm going to be putting that in the context of cellular mechanisms and oscillations. This talk is going to be technically correct, but I'm not going to be very technically demanding, so I'm going to keep things at a very high level. Okay, so first of all, we need to describe what tACS is as far as its dose, or tACS dose. And as with other forms of neuromodulation, tACS dose is just described by two things. The first aspect of tACS dose is where we position the electrodes. And these are just some example placements of where you could put an electrode. And remember, with all electrical stimulation, there's always two electrodes. So we have to describe where we're placing the electrodes, the size of the electrodes, and their shape as well. That's the first aspect of tACS dose. The second aspect of tACS dose is the waveform from the stimulator that is being played into the device, from the stimulator is being played into the electrodes and so into the body. And with tACS, that waveform is specifically a sinusoidal oscillating waveform, which has to have a certain frequency. It needs to be on for a certain period of time, and it needs to have a certain amount of intensity. If you specify those two things, you have fully specified your tACS intervention, and it's important to keep in mind that just like any other form of neuromodulation, tACS is not one thing. If we change the position of the electrodes, if we change the frequency, if we change the intensity, we have a new dose, and therefore potentially new effects on the body. So as we unpack that a little bit more, when we talk about intensity with tACS, we need to realize that this thing is wiggling. So its intensity is not the same all the time. And so when we describe the intensity of tACS, we're talking about how intense it might be at its peak. And so we just can describe the intensity of tACS as 1 milliamp peak, meaning the biggest it's going to be. Now, sometimes people will, instead of talking about peak, will talk about something called peak to peak. So you need to imagine that the signal is going up, back to 0 and down, back up and back down. And so you have 1 milliamp peak going this way. It's dropping minus 1 milliamp going this way. So minus 1 to plus 1 gives you 2 milliamp peak to peak. So you can use either one, they're interchangeable. For tACS, the peak to peak value will be double the peak value. Now, in addition to wiggling on and off, it wiggles for a certain period of time. And with tACS, just like tDCS and other forms of transcranial stimulation, we tend to leave it on for several minutes. So we might describe tACS as having a peak intensity of 1 milliamp and going on for 20 minutes. Now you can then say, alternatively, I want to increase the intensity. So let's say we go, for as an example, from 1 milliamp peak to 2 milliamp peak, all right? So now it's not the same intervention anymore. And if you remember what I said earlier, 2 milliamp peak is the same thing as 4 milliamp peak to peak. So now we've changed the intervention. We might do something else. Instead of leaving it on for 20 minutes, we might leave it on for 30 minutes. So you can see, so therefore, when you're reading a paper about tACS, when you're designing a tACS intervention, you have to be aware of how long it's going to be on and what the intensity is. Now, when we talk about how we increase the intensity and what the outcome would be, let's say you're trying to change behavior, you're trying to change cognition, one simple way to imagine it is that as we increase the intensity, we produce a bigger outcome. So this would be a linear dose response. So let's say we go from 1 milliamp to 2 milliamp peak, and whatever it is we're looking at, let's say reaction time, similarly increases, right? So this, or a decrease in depression mood scores, whatever it is, this would be a linear or monotonic dose response. This is not the case in reality for tACS. It's not the case that increasing the duration or increasing the intensity necessarily gives you simple outcomes in a monotonic or in linear fashion. So this is something else we need to keep in mind. We have different doses, and more is not necessarily more when you're talking about the response of something as complicated as the brain itself. Now, I've already mentioned this concept of frequency, and this has to be paramount when we're thinking about transcranial alternating current stimulation. The AC refers to a sinusoid, and the sinusoid must have a frequency associated, so that's that wiggle. When we talk about the frequency of a sinusoid, what do we mean? Let's say we have a sinusoid that wiggles up and then comes back down and returns to where it started, and that takes a second. And then that process again repeats for another second, and then so on. So every second, we repeat the process. That sinusoid has a period of 1 hertz. The period is the amount of time it takes to repeat. Another way to express that is in terms of a frequency of 1 hertz, or ones per second. Every second, it will go up and down, and up and down. So that would be a 1 hertz sinusoid. Let's say instead it wiggles faster than that, 10 times faster. So it goes up and down and up and down and up and down. And it wiggles 10 times in 1 second. 10 times per second is 10 hertz. So that's how we go from the rate of wiggles to the frequency. And you can imagine that the faster it wiggles, the period is also decreasing proportionally. But it's easier to think about frequency instead of period. So with tDCS, there was always a wiggle rate and there was always a frequency of stimulation. And the reason the frequency is very important is it's considered to be very prescriptive of what the stimulation will do to the brain. Why is that? One reason is that the brain itself generates its own wiggles or oscillations. Now you may have heard of these. People talk about alpha, people talk about slow wave sleep. These are the brain's own wiggles. It's endogenous oscillations, and you can record them, for example, with something called an EEG. So the brain is generating its own regular or somewhat regular oscillations. The theory is that if we apply tACS on top of the brain's ongoing oscillations, we can influence them and specifically enhance them. And one step further, the best way to do that is by matching the frequency, the rate of wiggle, of what we apply to the endogenous frequency, the rate of wiggle on the brain. So if the brain is, let's say, wiggling, oscillating at 10 hertz or 10 times per second, and we want to enhance or boost the brain's 10 hertz oscillations, we will stimulate at 10 hertz. If the brain is oscillating at something like 50 hertz, then we will stimulate at 50 hertz. So the theory is that matching the frequency of stimulation to the frequency of the brain's ongoing oscillations will produce a synergistic effect. So you see why frequency is a really important concept when we're talking about tDCS. Okay. Now, I want to talk a little bit about polarity. And to do that, I'm going to take a step back and I'm going to talk about transcranial direct current stimulation. And I'll do that a few times during this lecture because I think conceptually sometimes it's easier to take a step back when we go forward. So as I've talked about in other videos, with tDCS, we also have 2 electrodes. We have a positive electrode and we have a negative electrode. And the name of the positive is the anode and the name of the negative is the cathode. Now current comes from the stimulator and arrives at the positive electrode. It enters the brain, it travels through the brain, and then it exits at the negative electrode. So now what we're seeing here is a computational model. It's sort of predicting what's happening in the brain. Here we can see a transparent view into the head. Here's the anode, here's the cathode, here's the brain under it. And in this picture here, the hotter colors show you where the current is flowing. And you can see that under the anode and under the cathode, we both have, in both cases, current being delivered to the brain, right? That's the hot spots of current flow. But in this plot here, I've done something a little bit different. I'm representing the direction of current flow. Now under the anode, you can see the current is flowing into the brain, right? So you can imagine it's arriving and entering the brain. So from the perspective of the brain, it's washing in. Under the cathode, the opposite is happening, right? Current is being drawn out. And so even though the intensity is the same, the direction is different. And again, this is something I've described in other videos focusing directly on tDCS, but it's important to think about this concept in the context of tACS. Now again, what does this directionality mean as far as neuronal polarization? Well, if we imagine that here we have our cortical neuron somewhere around here, and then we're going to imagine what's happening when we have this electrode over it. Initially, we're going to be thinking about what's happening under the positive electrode. If you remember, that's where current arrives at the head, and so it's sort of washing into the brain. This is the direction of washing in, and this produces a depolarization of the soma. And I'm going through this very quickly. My other videos describe this in much more detail. What I want you to appreciate here is that if we look at the other side of the head, which is now the cathode, the direction of current has reversed. And because the direction of current has reversed, the polarization has also reversed. And in this case, we're producing soma hyperpolarization. And whereas the anodal variant is considered to produce an increase in excitability because of the soma depolarization, the cathodal variant is assumed to produce a decrease in excitability. And I'll be, I have a couple papers I'll be citing, and I'll be putting links to them below if you really want to dig into this in much more detail. So this is the summary for tDCS. What does that tell us about tACS? Well, if you remember with tACS, what we're going to have is a situation where the current is wiggling, right? It's going in one direction, and then it goes back to zero, and then it goes back in the other direction. The way you need to think about it is, at one point in time, this is going to be the anode, and this is going to be the cathode, and that means the current is going to flow this way. However, at some point, those are going to flip. That's when the oscillation goes from one polarity back to the other side. So when that happens, whereas before this was positive and this was negative, now this is positive and this is negative. So before the current was flowing this way, now the current is flowing this way. And that happens within one period or one cycle. In the next cycle, you get this flip again, right? Anode cathode this way, then anode cathode this way. So I want you to imagine current's flowing this way, then it's flowing this way, then it's flowing this way. And this flip is ongoing as long as we have the tACS on. Now, how often does it flip? It flips at the rate of the frequency. So that's how we're flipping back and forth every time. And so in this case, you can't think of it simply as having an anode or a cathode, because there is no fixed anode, there is no fixed cathode. When we describe tACS, we can't say that's the anode and that's the cathode the way we do with tDCS. With tACS, the anode and the cathode are always switching back and forth, and so we don't describe that, we simply say what's going on. Now, let's visualize what this means at the level of the brain. And so what you're seeing here is a computer simulation where the colors are indicating, let's first think of it as the colors are indicating the direction of current flow, with red meaning in and blue meaning out. And you can see that they're flipping back and forth. Now the rate of this video is a bit arbitrary, but this relates to the frequency of the stimulation, right? The faster the stimulation frequency, the faster you'll see the slipping back and forth. And so we have current flowing in, current flowing out, current flowing in, current flowing out. Another way to look at these colors as representing the polarization of the soma, because red in means soma depolarizing, and blue out means soma hyperpolarizing. So you could also think this visualization is showing you soma depolarizing, soma hyperpolarizing, soma depolarizing, soma hyperpolarizing. Every time we're flipping that direction of current flow, we're flipping the direction of the polarization of all the cells. All right. Now I want to note here something that I've sort of been glossing over until now, but if you've been paying close attention, you've seen it. That when the soma hyperpolarizes, depolarizes, the dendrite hyperpolarizes. Or conversely, when the soma hyperpolarizes, the dendrite depolarizes it. This is something I've discussed in the context of tDCS, but for our purposes here, I do want us to focus on the soma as sort of the driver of the outcomes. And again, I think it's really worth representing it in different ways. Here again is this notion of current flowing in or current flowing out, or if you want to think about it as depolarization, hyperpolarization, depolarization, hyperpolarization. Now where it happens, right, where it happens depends on where we put the electrode and how big the electrode is, but the rate that it happens at will depend on the frequency of stimulation. Here's another representation as well. Now we're looking from the sort of top of the head as this is happening. By the way, the electrodes in this case are across the front. Well, you can see the montage right there. One is here and one is there, so the current is flowing in this way. And one thing I want to draw your attention to here is it's not just red, like in one whole area and then blue in another area and flipping. There's a bit of a zebra pattern, right? You can see here, there's like a red and then a blue and then a red and a blue. And the reason that's happening is the brain is very folded, and as the current cuts through the brain, it's going to go in and out of a gyri. And so you produce this somewhat mixed pattern, and I'll be going back to that in a little bit. It's true for tDCS, it's true for tACS as well. And finally, let's zoom in one more time. Now we're really looking at the level of gyri. Here you can see these little arrows. The arrows, in addition to the colors, tell you the direction of current flow. So you can see it's direction, back, and so on. And this direction reflects an inversion of the direction of current flow, but also an inversion of the polarization that you see. And I've spent a little bit of time on this because this is a really essential concept for tACS. Okay, so the current is inverting, it's producing a polarization that also inverts. How much polarization is produced during tACS? This is a big concept, and once again, I'm going to drop back to the concept of tDCS, or direct current stimulation, because I think that is a good way for us to get intuition about what's going on before moving on to tACS. And I've described this a bit in my other videos that I'll link to at the end, and as well as the, if you really want to get into it, I'll be linking to some references that you can really dig into. But the general notion is that when direct current flows through, you produce a polarization. And you can see here that the polarization does invert. So in this case, the current is flowing in the downward direction, so it's producing a soma hyperpolarization, but a dendritic depolarization. And if the current were to flip direction, so would the polarization. The stimulation is turned on from here to here, right? From here to here, where this line is. And so it's polarized when we turn on the device, and then when we turn off the device, it goes back to the way it was before. But if you look very closely, you can see that there's a little bit of a transient when we turn it off and when we turn it on and when we turn it off. What I mean by that is that we produce a polarization, but it's not instant. The polarization seems to lag when we turn on the stimulation by a little bit. So we turn on the stimulation, and then the polarization starts, and then it reaches some sort of steady value, right? You can see it right here. It starts, and then it reaches some steady value. And actually, when we turn it off, there's also a bit of a lag. It doesn't immediately go back, right? The stimulation is off here. It doesn't immediately go back to where it was before. It takes some time to go back. We describe that lag in terms of, one way to describe it is in terms of a time constant. That time constant tells you roughly how long the system needs to respond, and it depends on the cells and the compartment, but it's around 10 milliseconds, can be a little bit less. So the system doesn't respond right away. By the way, why is this? It's if you're familiar with circuits, you could think of the cell as a RC circuit, so that's where that lag comes in. It's essentially acting as a low pass filter. This has a lot of important consequences for this question I wanted to start with, which is how much polarization you produce. And this is why. Let's say we were to do a DC stimulation, right? So we turn on the DC, and then what happens to the polarization? It doesn't start right away, but it starts to polarize, and it eventually gets to where it's supposed to go. Okay. If we double the amount of DC we put in, we actually going to get double the amount of polarization, 10 times the amount of current, 10 times the amount of polarization. All that makes sense. And it's roughly 1 millivolt of polarization or less for every 1 milliamp we put in, right? So you can imagine 1 milliamp gives you 1 millivolt of polarization. 2 milliamp will give you 2 millivolt of polarization. Imagine if we turned it on. Let's go back to the 1 milliamp example. We turn it on, and we're starting that polarization process at 1 milliamp. It's heading towards 1 millivolt. But before it gets there, we stop. We turn off the stimulation. And so it relaxes back to where it started. It never got to 1 millivolt. Maybe it only got to half a millivolt. And so if the stimulation is only on for a brief period of time, because the membrane has this lag, it won't fully polarize. It won't fully reach its potential, right? Because it doesn't have as much time. In fact, if I were to turn it on and turn it off really quickly, it might not have any time to respond at all. So the polarization we see under direct current reflects having it on for a long time. Now let's think about tACS. With tACS, what do? We turn it on in one way, and then we actually turn it off, and even pull it back the other way, and then turn it back on and turn it back off. And so it's the same notion as not having it on for a long time. As the current goes up one way, the membranes start to track that polarization. But then it's over and it comes back to zero. And then it starts to go the other way and it starts to push the membrane in the opposite direction, and then it goes back up the other way. So even though it's on all the time, it's pushing this way, it's pushing that way, it's pushing this way, it's pushing that way. And if it's too fast, the membrane can't track. That is why there's a delay here that you see with direct current. Is very important to understand what you will see or what you won't see with alternating current.